think I was muted. So good morning, all. I just thought I'll start here with some just a quick hint, I would say, of what is important for the up and coming midterm, and having just a good understanding of 9.10 over here is gonna help you. And yeah, I did mention as well, for depending on the steady state operation or not, you'll end up with 9.15. But if that's not the case, you can obviously look at your mean and your mean moments and mean torque. And obviously the alternating ones. So just be familiar with this, and don't be surprised when it comes up in the midterm, and how to apply them. They're fairly easy. So yes, I thought I'll mention that. Just sharing something with myself. Cool. So let's dig down onto the continuation of rolling bearings. So I'll just unshare this and then I'll go to the slides. Okay. Are we? Yeah, okay. Unshare that, and we can proceed with the lecture. Okay, so we've discussed, the functions of bearing. We are aware that there were different types, and now we are moving on to the most common type, which is called rolling bearings. Obviously, I've mentioned this before. Um, they're very common. So just when you're comparing that to your your journal sliding bearings, let's look at some advantages they have over them. One, low starting and good operating friction torque. So that's great. So at starting, and even at operating, our friction torques can be a lot less, right? Obviously, this is due to this rolling element, ease of lubrication, reduce axial space, and generally, they take both radial and axial loads. Unlike your journal bearings, where all your radial loads was it's the main load taken. Quick replacement. There's also a warning of impeding failure by, so you'd hear the bearing makes a noise, and it'll tell you that it's ill, so we have to replace it. And then obviously good low temperature starting as well. Some disadvantages are greater diametrical space, more space. It, Also, there's alignment issues that cost more, some noise operation, the finite life, eventual due to fatigue, and ease of damage by foreign matter, and poor damping ability. So if you remember when I showed you that article of the wind turbine bearing failure, you would maybe I should just quickly look at that. Just want to open the chapter. I can quickly share. Obviously, you actually have a case, let's say a case study, but could have some, I guess, practical perspective on this. So this paper I did present it in the last lecture. It's not published by me. It's published by these authors, and it talks about wind turbine bearings failure analysis and fault diagnosis. So obviously why wind turbine bearings fail and how can they diagnose their faults. Now, there were several possible reasons why. I did showcase this as well. We're talking about you direct your one with a gearbox and one with a direct drive, two different wind turbines, and they're just showing you where all the different bearings are, just to illustrate you how important bearing as a mechanical element is. And this is your direct drive over here. There's no gearbox, and there are pitch bearings and main shaft bearing. Got your bearings as well, and you generate the bearing over there. So, nevertheless, there are several causes of why um, these bearings fail. These authors have established all of this in a nice review paper, and you'll notice over here they'll talk about local. There's a few faults like general surface plastic deformation, local surface plastic deformation, indentation, and all on those bearings you notice these deformities, so to say, which are obviously causing bearing failure. Obviously, in case of any important, you can see there over here corrosion as well on the actual ball of the bearing. So like it's quite classified in this paper. It's on the groove as well. There's this some corrosion as well, but the main was the one I showed was a lubrication and whether we have insufficient lubrication or over lubrication or with the lubricant's contaminant, this all caused um you know the bearings to fail, and these are the factors we have to consider. So there's some insufficient lubrication over here. So I just thought I'd mention this. I didn't mention it in the last lecture, but just in the case of wind turbines, thought I'd mention that. Okay, so what do we have? What does a rolling bearing look like? I believe you've all roughly seen this. We have I have a demonstration now of where we have outside the diameter of the bore to the shaft footing. There's an inner ring, there's an outer ring, and we have the basically the so well there's the inner ring, right? And then we have the bore race, that's where the bores are going in, or depending on which element it is, but then we also have the bore shoulders, the face of the bearing. So yeah, these things you can obviously have a look at, but I'll come back to this now. And there are different types where you have your for the ball bearings, you have deep groove, you choose contact bearings, you've got double row, you've got angular contact, um, self-aligning thrust bearing, and self-aligning thrust. Some roller bearings. So roller bearings would have a cylindrical type of element, not a ball. And those are the different ones over there. I think I probably I'm just still thinking now. I had a diagram and I'm not sure. Okay, cool. So yeah, this is what I mean. So there we have a ball bearing, a roller bearing, needle, all these different types. Needle roller bearing as well. So we're looking at these ones where we have that this rolling element now. So these are the bearings we're looking at. But there was a catalog I initially had. I don't think I showed that video, but it was illustrating. I'm realizing now the different of the multi-grade oils and the different viscosity. You can actually see which one is, in terms of viscosity, which one is better. So that was quite interesting. But anyway, I can't find this chart for, I'm not sure why. Nevertheless, based on the catalogs, um, you you also you put when you get a catalog, it'll essentially look like this over here, where you have the bore, dot diameter, width, fillet radius, and then these important parameters over here. So in this case, we're dealing with a 02 series ball bearing, and we've got the load ratings here. So your C would stand for your dynamic load rating, and CS would be your static load rating. There's something also called the rating of the life rating as well, which we actually compute based on these values. That's for your ball bearings, cylindrical bearings, depending on what series you're working with. You notice nearly basically the same type of thing, where it's 2 series, 3 series, and your your dynamic rating. What's also important of bearings, we don't take it, we don't use okay, you don't use charts essentially, we use tables. And we have to compute this thing called equivalent radial load, right? And it's essentially the radial load on the bearing that has the same effect on the bearing life as the applied loading, right? Its formula is given as some value x times v f(r) plus y times fa. What you'll notice there is that there are two um, loads, your actual radial. You've also got this rotational factor v, depending if there's a inner rotation, right, of the ring or an outer, you have to modify for that. And those x and y values, the radial and thrust factor, are all computed through a table, right? And then your KS would be like your service factor, which I believe, or shock loading factor, sorry, in this case. And they are given in tables. So like XY there will depend on the number of balls or rollers or all the diameters. So it's factors, but all comes in tables, which is easy. Here are some typical service or shock factors. Once again, I'm not sure where these values come from. I'm not sure if people have done experiments or these could be accepted design norms. Of design, we're always applying these design factors, safety factors, service factors. And this is those factors which I'm talking about. I'm just having a look here before we actually get to where we need to get. Okay, cool. I do want to show you the illustration as well. Nevertheless, so for a deep groove ball bearing, that's a table I'm looking for. So in relation to this over here, this is kind of going through the procedure on how to do this. We need to look at the actual load divided by our static load. We need to find E, which is a variable reference value, which will determine which of the X and Y so-called factors as mentioned here, which is your radial and thrust factor, um, which we'll be using in the equation. So we need to find this and determine which, of these factors. And again, these factors depends on the elements, sizes, things like that. When we look at for your angular contact bearings, which look like that. And yeah, we apply a similar type of thing. And we have to see first determine with single roll or double roll. And we got to find that so-called E, the variable reference factor, which will determine which X and Y factors we will use. So that's essentially yeah, the main approach we're using. Then in terms of selection, there's a few things we want to look at, and I'll try to do around 2 examples. One will have like some small continuations, and the rest you don't like it to continue with. And then the other one is how to select a bearing depending on the loads. Ties into chapter 1 in a way. And here, in terms of selection, so each group of familiar technical bearings must suffer slightly metallurgically surface finish, or it's not all made the same way. They say no two bearings within the same family can have the exact same number of operating hours to fatigue failure. And so they're saying, therefore, the selection of bearings is often made from tables or standard types or sizes contained from data of the life and load ratings, right? So if we look at this formula, this is that life formula I was talking about, which is given in 10 to the power 6 revolutions. Obviously, this is probably coming from some experimental tests where they run several bearings, I believe, I'd like to believe, and they can estimate the life of the bearing. From the life equation, you can also get the amount of hours, which I'm trying to figure out, which I'm not seeing over here. Yeah, which eventually you can get the amount of hours as well. You know, of the bearing. Oh, it's over here. Yeah, this should be the life in hours. So what's key here, you see, is your basic load rating from those tables as mentioned, 10.4, 10.5. You've got your equivalent data load, which you have to compute using that formula over there. And then you'll notice we have a parameter depending whether you're going ball or roller. And yeah, that's a factor. If you're going ball or roller, specified in the question, you have to apply that to the formula. And obviously you can compute this in terms of hours as well. And you'll notice in this difference between these two, you've got the 60 and you've got the N as well. The rotational speed, and obviously we divide them by 60 to get it in hours. Let's say generally CS, the static has a little effect, static factor has a little effect on the ball and roller bearing selection, unless the machine stopped for a long time, right? So bearings cannot operate at low speed under, yeah. The dynamic load rating as well, that's the base one of the main ones, and that's in conjunction with the rating of the bearing at a certain ability, which is something which we'll talk about now. And they're saying, yeah, what bearing reliability basically is the likelihood of a bearing to operate properly for a given period of time, right? So that's what it is. It's basically on the chart over here. As you can see, reliability is fairly high, and then life adjustment factor. So one must be cautious of R5 and R10. That's the rating life, and this is now the rating, it's the rating life, and this is the rating life at 5, but one should be, I'm just thinking now, so that's at 90%, and for reliability greater than 90%, we have to use this formula. I'm just getting confused now. And then there's a life adjustment factor one must account for. So if you had a 95% reliability, if I pull up the graph over here, your life adjustment factor is basically 0.6. So this is all when you have 90% or greater, or greater than 90%, then you're going to have to use this formula instead of that one. This is typically specified in the question. All right, so before we embark on solving this question, let me just do some quick, that's what I'm looking for. Yeah, the demonstration which I mentioned I wanted to do in terms of the bearing. Okay, second. So I just wanna unshare, and then I wanna share two things, and then we'll start with the standard solving of problems. So where is okay, it's opening up. Then what I also want to do is find this catalog. So, all right, so what you might see is this, might see a bearing. That's what it looks like. I'm sure everyone has seen it. Something like, okay, there we go. I'll get back to the catalog. But obviously you wanna have a look inside it, right? So you're gonna open them up, and we can actually see all um, those things I was mentioning. Just zoom in a bit, where we've got the steel ball over there, right? We've got the inner ring, then it's the outer ring as well, which is that. That's where the ball is housed in. Um, and then let me it's quite cool. Then you can actually, that's the sketch I had earlier on. Let me just, I don't know why I'm able to rotate this thing the way I wanted to. But yeah, that's what I was looking for there. Just zoom in a bit. And you can see the steel ball, the separator. Oh, let me just go back a bit. Um, Ball outside diameter seal. Yeah. So yeah, cool. So then if I just actually do that, and you can actually see what it looks like as it's rotating. We've got the inner ring, and then we've got the outer ring over here. Let me just see if I can, that's just closing it up. So yeah, so the anti-friction ball bearing, right? It allows bearings allow humans to move an object within another object, right? Yes, yeah, or engineers in this case. The main purpose is to extract desired motion from a whole motion. For example, a pump shaft that passes through the pump housing should rotate, but the housing should not rotate, right? So this should move, other parts stay stationary. Almost all machines operate within some form of rotating or sliding or oscillating motion. When this occurs and bearings are used, ball bearings are probably the most widely known bearing and easy to identify, right? So saying this type of bearing operates upon one contact with one stationary, usually the outer ring and the one rotating ring. Your inner ring, cool. So let me just pause him. And your inner ring forms the inner part of the anti-friction bearing or rolling bearing, the part that pushes against the shaft. And the inner ring is also known as the inner race or cone. The term cone is usually reserved for tapered bearings, right? If you know taper, it creases, it converges. Yeah, then we can look at maybe what's next after that. Outer ring, that's outside part, right? Also, they call it a cup. We have the rolling elements, and again, you can have different types of rolling elements. And then the separator, yeah, which the separator cages spaces the rolling elements apart from one another. So I just thought it'd be cool. I'll send you guys the link for this, and yeah, you can play around um with this great company. Savvy doing great things for engineering work. So then after that, before we embark on that, we're going to look at um, what is this? The catalogs for bearing selection, right? So you've got your SKF, um, one of the main companies for bearings, and you also have your Timken as well. And I believe they are an American company. And SKF, let me just check here, it's going to be European, eh? Um, well, obviously they have a massive company. I'm not sure where they've started, um, but it's a big company. It's one of the main brands in bearings, and it's probably worthwhile downloading this catalog and looking at it. So I just thought before I actually start on the analysis of the bearing selection, I did show this to the class previously, and so they stapled it all, your angular contact. Um, there was a cool illustration of why we need elements. I just want to get it quickly. Yeah, like the basic principles, right? It's always worthwhile reading these things. Um, okay, like for instance, wire rolling bearings, right? And they show a cool illustration of if imagine we had a block against a surface, and as we load, there's some sliding friction, obviously. And to make that easy, we add some rolling elements. That's the essential concept of a rolling bearing, right? And then They talk about ball. It's a ball bearing roller, which is a rolling bearing, as we can see. There's a little one. They say over here, the balls make contact with the ring raceways. Figure 2, you can see over here. With increasing load acting on the bearing, the contact point becomes an elliptical area. The smaller contact area provides lower friction, right? Which enables ball bearings to accommodate high speeds but also limit their load carrying capacity. Very important. Whereas your rollers, on the other hand, look there, with the increasing load acting on the bearing, the contact line becomes somewhat a rectangular shape. Because of this, you have a larger contact area, have more friction. However, it can accommodate um, moderate to heavier loads, but lower speeds, right? Than the same size bearing in terms of, I guess, its volume. So that's quite interesting. And then we also have your rolling bearings can be classified to radial ones. So they basically these ones they mostly accommodate obviously the radial loads, but sometimes it can do axial loads as well. Let's say in one direction in some cases, whereas your thrust bearings are predominantly for axial, right? That's an axial load over there. I know we discussed this over here. And yeah, the thrust bearing for an axial load, you can see what it looks like. They have one at the angle. I showed you that before. So these are quite cool from the actual bearing manufacturer. And there is an ISO standard for all the vocabulary for all these things, right? We obviously we had to look at that. And then there's so much to look at, but I wanted to take you. It's also it's even selecting the proper grease and lubrication. That's some extra charge. We're looking at I'm not sure what this one is. Like similar to your summer fuel number and your life modification factor. This is for fatigue now. Yeah. And we don't actually do this, but if you look at this formulation, sure you've seen it before just now. Um, the same factor. And of course you can see over here. So of course the design 3 subject will give you a good introduction to it. However, when you do get into it, there are other specifics you need to account for. And typically these guides will provide yeah, they'll provide the necessary detail. There's something I'm looking for. It was on the catalog, and you'll notice it's nearly the same, but these are the calculation factors, not these ones. Yes, this is single. Yeah, yeah. There you go. Then you have your dimensions, your basic load ratings, dynamic and static, C and CS. There's a fatigue load limit as well, which we don't look at, but that's a factor within the bearings, the limiting speed ratings, and so forth. And they recommend you certain bearings. But it's very important also when you're designing a bearings, obviously the inner diameter, and the bore, how you actually going to fit the shaft in. So that's for single row. So yeah, so it's worthwhile looking at these catalogs as well, to get the actual experience of what this looks like. That being said, let's revert back to the calculation. So what we're going to try to do is solve this problem. All right, it's in your textbook. It's not generated by me. And yeah, let's give it a go. Good, cool. So okay, it doesn't look so good. Let me just go back to the textbook rather. I'm distracted there. Hmm. So luckily, we don't have to worry about too much about lubrication here. Rolling bearings do get lubricated as well, but in terms of analysis, in this case, it's they deemed anti-friction, you know. So okay, I'm nearly there. Um, there was something interesting in the textbook as well, but that's fine. We can always look at that again. So here we go. Oh, yeah. So here we have a question. Determine the median life of a deep groove ball bearing. So it's a 50 mil ball bearing. Um, Trying to figure that. You obviously can imagine what it roughly looks like. Carries a load of 9 kilonewton daily and 6 kilonewton actually at 1,002 RPMs. We need to determine the equivalent radial load and the median life in hours, right? So to begin, what is important is I want to just copy that formula so it's always in your mind. It's basically the fundamental formula for bearing. So it's this guy I wanted to always think about. I'll paste it over here. And then it is your life formula, right? And obviously you must be aware that's also depending on your reliability. So I'll just put these ones just like that. So these are what you always have in mind. You're trying to essentially populate these guys. And as I've said before, um, these these are all of these calculations. Their sole purpose is to allow us or enable us to make an effective decision when we design it. Right? Might not be perfect, but yeah. So before we begin, let's quickly see. So I'm just trying to see something. So what we're gonna assume for this question, right? As per the because we need to assume something here, and we're assuming in this case for now we have the inner ring rotating, right? And the load is steady. Perfect. Okay. So remember, it's a factor we need. So the first thing we want to do for the question is look at our catalog of the 02 series deep groove ball bearing at a 50 mil ball. All right. So what I'm going to do, I'm going to get the table and we're going to have to pull some values from it, right? So just be very cautious that depending on what bearing where it's going to be ball or roller bearings, you need to look at the right table. That's very, very important. Um, and each is equally examinable. So don't think it's all about balls every time. Quickly just make that small. Cool. So I said it was 50 mil 02 series, right? So 02 series, here we are. Look at a 50 mil ball and we need to pull up some values. In this case, that's going to be your dynamic and your static value. That's going to be 35.1 and 19.6. So those are the values you're going to want to extract, right? So then we're going to say your C equals, what was it again? 35.1 and then 35.1 and your CS equals 19.6, right? Cool. That's obviously gonna help us with our thing. Once we have that, we now need to check for our factors, right? You'll see where it comes from now. Just looking for something quickly. Okay. So we need to find that X and Y value, right? And we now need to go to table 10.6. Okay. Now, what I did not show you, or didn't mention it, is that the other equations matched to this is also this one over here, which is kind of the same thing. Just we have a service factor times, and if there's no actual load, then we just can kind of omit that part and be left with this over here, right? So I'm just making aware that these are all, yeah, these are all the possibilities over here. But in this case, I'll leave steady, be cool. We've got these, and now we need to start finding the radial and actual factors. Okay, so let's quickly try and do that. So you want to go to another table. This is table 10.6, and you'll see them now, 10.6, right? Okay, and so I'm just gonna paste that table over here. So if I do that, as you can see, what we need to do now is find FA divided by CS, right? That's the first thing we need to do. Once we have that, we need to find that E factor, which I've mentioned before. Based on that E factor, we're then going to distinguish whether we over here or over there, right? Then these X and Y factors depend on a few things. As I mentioned before, I mean, I'm not always sure of these things all the time, but that's the idea. So let's quickly find FACS, and then we can find E. Typically, what is done, we can find these two immediately, but let's just go like that. So let's find FA over CS. So FA divided by CS, which is going to be your actual load given, of 6 kilonewtons. And then we're dividing that out by 19.6, right? If you do that, let me just check my I'm working here. Um, let me see. Yeah, you should get an answer, I believe, of 0.306. Cool. Once that is done, we then now can find our E, right? As I mentioned to you before. Let me confirm these values. 19.6. So let's find out our E value, okay? So to find E, we need to obviously have a look here. So our value is 0.306, and that falls between these values over here, right? So therefore, we got to conduct an interpolation to find E. So let's quickly set that sophomore table up. Obviously, we use a linear regression using our calculator, I believe. Let me just set the table up like this. I'm sure we're all familiar on the Casio. So it's 0.28, 0.42. Let's confirm here, and 0.38 and 0.42. Okay. Cool. And then 0.42. And of course, we're interpolating for E at 0.306. So if we do that correctly, let me just check. Just share my screen here. So I'm just probably doing this one interpolation now, and then the rest you guys can obviously do yourselves. There are third year students after all. So 3 stat, 2, and we can put in those values, 0.28, 0.38, 0.42, 0.4. Cool. Chef stat 5, 5. And then we're looking for 0.3 0.06. We then interpolate and you get an E value of 0.3874. Okay, it's all coming from here. I believe that's correct. Cool. Once that is done, some very basic algebra here. Let's quickly see. We then must determine that other factor, like I mentioned, right? Which is this FA divided by VFR, right? And we got to see which one it falls equal, less than, or greater than. Let's quickly do that. So that's FA divided by VFR. Let me just confirm. Yeah. So let's quickly do that. So this should be equal to, actual load is given as 6. Now that V, if you recall, is dependent on whether there's a outer ring rotation or inner ring rotation. And so that means, yeah. So let me just quickly check. I'm looking for that part so you can see. Okay, let me just have the book here somewhere. Open. So that's, and I just have to unfortunately cross 2 chapters. I just want to show you so you really to be conscious of it. And you can see over here, depending on the rotational factor, depending on whether it's inner, it's 1, if it's outer, it's 1.2. So be conscious of that. So in this case, we have 1, and then our radial load given was given as it's 6 and 9, eh? Okay. So we have 9 over 6, you get 0.67. So if you compare this to this, we find out that if a VFR is greater than E, right? And if that's the case, we're falling over here. We're on this side over here. So it's cool now. We know our 1x value is 0.56, right? However, we now need to compute, that's our actual, I think, our radial. Now I have to find our actual factor. But now we need to interpolate to find our y, right? So what we're going to do now again, we have to now interpolate from 0.2 to 1.15, and then from 0.42 to 1.04. Okay, so I'll do that. That's based on table. And we know x is going to be, what did I say it's going to be? 0.56. So then setting up our so-called interpolation table, that's 0.28, 0.42, 1.15, and 1.04. And you're interpolating, should remember for y, which is this over here. And I'll just say y at 0.306 again. If you remember coming from that, and you'll find that y should be equal to 1.13. So that's perfect, right? Once that is done, you then have to obviously now come to the equivalent radial load formula. That's what's key. And as you can see, we're going to have to use this one over here. Do we need to use a service factor? It says the load is steady. So I think a service factor that is 1. Yeah, so we don't have to worry too much about that. Just be aware of it though, that depending on your, that can affect the equations. So let's quickly try and do that. So this is our equivalent radial load. Let's compute that. That's going to be P equals Ks, then it's X. Forgive me, V FR plus YFA. Okay. In this case, it's sum 1, load is steady, x is 0.56, inner ring rotation 1. FR was given as 9 plus 1.13 times FA, which is 6. Quickly compute that. Plus times 9 plus. You should get 11.82 kilonewtons. Perfect. So that's our equivalent radial load. Another check you probably what you want to do is check which of the radial loads are longer, and I particularly mean by this part over here, which is essentially that part over here. And if you do that anyway, you find that P is actually going to be 9 kilonewtons, as we've said before. So you want to actually check which is more. And based on that formula, I'm making you aware of that. But typically, this should be more. That's the case. Once we have this guy, we then come up to, oh, then we found A, which is the equivalent radial load. Perfect. Cool. We can just do this. And then now we're at B, we're going to do the life, right? Just do the life quickly. B the life, and life is given as that formula, right? Again, we must be conscious that depending on the reliability, which in this case they didn't really mention. So there, 10 to the power 6, we have 60 times the rotational speed. I believe that should, can that be an RPM? Let me just confirm quickly. A small n typically means revs per minute, right? Let me just confirm. Yeah. I think we can put in the 60 makes that. No. Okay. Anyway, let me just have a look. So I'll say 1,200 to begin with. Just got to check the units again. C, which I think we got, and that C was what was our C again? 35.1, right? Let's put that in there. And then we have to divide this by P, which is our equivalent radial load, which is 11.82. Then we have A, right? And if you remember what I told you about A is dependent on whether you're dealing with if it's let me just put it up for you now. If it's gonna be ball bearing or roller, I believe we're dealing with ball bearings, so we gotta adjust that. So that's gonna be 3, power 3. And let me just compute this and see what I get. So typically you want to work out the median life first, and then you get it in, you can do it in cycles or hours. So I'm just getting the hours one time. Let's just do, and then 3, and then if you get that answer, you should get around 363.69 hours. And what that tells us is that that's the amount of hours. But when you talking to the so-called, yeah, so that should be sufficient. And then they do, let me just see here. When you do the 5, L5, and well, that's the reliability. I think that's sufficient for now. I don't want to take it from there. You notice in the question there's a separate part where they do that. Now, the next part is basically, let me see, the, using now an outer ring, but then an outer ring, but then and then it has some moderate shock. So that's another but what I wanted to add was this part instead. Um and that is the expected life. Um so in 10.6, what they basically do now, they just change the conditions and say the outer ring rotates and the bearing subject to moderate shock. So I believe if you follow the same procedure, you should come out to the same answers, right? So that's what's key there. But what I want to bring was this part here, and this is now talking about the expected life of a bearing, and if its probability is 6%, if 6% probability of failure can be permitted. Okay, now that's to do with that other equation I showed you here, which I thought was worth mentioning. This one over here. Here we go. And the key here is um, if you have a 6% of failure, that means we have a reliability of 94%. Obviously, you can figure that out quite, it's fairly self-explanatory. There's something I'm going to talk about this part. I'll show you on Shigley's as well, but um, I think I'll do it after I'm done with this. So we have that, but once we have that, we then now need to check this table over here, and I'm going to get it for you. It's that graph which I showed you. Cool. It's the reliability factor, and we will place it over here, and we will try to extract the necessary value. Okay, just make that smaller. I'm sure there's a efficient way to change the size quicker, but anyway. So we got 94%. And as we go up the curve, you'll notice your life adjustment factor is 0.7. I think that's fairly easy to see. So now, I'm not sure of the notations of 5 and 10. I just have to look at Sheila again. So again, we know what our C was as per 10.5. I believe that was 35 point, we're basically applying this the same set of the same set of thinking here. But remember your formula, if you want to add, if you want to get that in hours, it's you want to say 10 to the power 6. It will be KR, right? 10 to the power 6 divided by the 60N, right? And then, of course, you put in the CP over A. So if we do that, that's going to be that 60, that speed was given as, what was it again? 1,200, eh? Or that's 35.1, I believe. And that was at 11,82. We're still dealing with that same bearing. And that's going to be, it's going to be 3, hey? Is it 3? Yes. And we can calculate that quickly. Try. Surely can't we take that same answer at times by 0.7, right? Can't we do that? Is there any other factor I'm missing? Yeah, no, so we can just take, we can just simply take this value, right, times it by 0.7, right? So we know it's going to be 0.7 times that 363 point, what is it? 69. And we should get an answer of 254.58 hours. And if you look at that, you can see that, look at the difference in times, right? And they do state here that to improve the reliability of this pairing from 90 to 94%, a reduction of median life of 1820 to 1275 hours is required. So you can have a look at that, but what's key there is that um, you have to change that median life hours. Kind of makes sense in a way. Cool. So that's that part there. So that's the main thing of pairings. I do recommend your job to do, and I'll share that with you now, is to go over where are we now? Go over 10.6, extending the life 10.7, right? In conjunction with that, go straight to the exercises and you can come over here. That's over here. And I recommend doing 10.22, 10.25 up to around 2.27, 2.28. So everything from there till there, that should sort you out nicely for the up and coming midterm. Um, then if reverting back to the lecture quickly, I used to be a big fan of materials. I think it's probably worth mentioning. But you can obviously have a look at the different um, let me just go back to my slides, the different materials required for the bearings um, as well. And let me just share and then I think I have it on my slides. Where I've mentioned this. Okay, this is my OneNote. Anyway, so just have a look at the different materials for bearings. But I think what I can do now, just open up Shigley. Then I'm going to do one more pertinent example, um, which I believe is like cornerstone of what what is supposed to be done in bearings as well. And always remember Shigley is the mechanical design Bible, right? Mentioned that to you before. Yeah, cool. So if I go to rolling bearings, there's a lot of proper detail here, and you find a few things which is important in terms of understanding. And I think I always teach in that way. I'll do the example and I'll come back. And yeah, we can look at just maybe look at this graph and then see what they say, and then something else I want to mention. So they say no, we normally identify groups of or tested of bearings to the life failure criterion at different loads. They plotted on two log scales over here, right? So let's say using a log-to-log transformation, of course, a log curve to establish a single point F1, right, at the rating group of 1, that are coordinates are logarithmically transformed. The reliability associated with this point, no other point is 0.9. Thus, we get a glimpse of the load life function at 90% reliability, right? So we get that curve. And then for many tests of bearings, they find out this. So this is important because, I mean, even in dealing with different types of bearings, this all becomes a factor. I'm sure magnetic bearings have their own curve. And then they say the catalog rating is defined as a radial load that causes 10% of the group of bearings to fail. There we go, that 10, right? we should denote the catalog load as C10, right? This catalog load rating is often referred to dynamic load rating or sometimes a basic load rating. If the manufacturer's rating life is 10 to the power 6 revolutions, right? So the radial load that would initially cause um, failure at such a low life would be like very unrealistic, right? So of course, you should obviously review this basic load rating. And here they essentially end up with that formula we found, right? L over DLR. It's nearly the same. And you could actually do yeah. So what Shigley does well is that it actually incorporates the probability, particularly the Weyl distribution. Um, and it's just another simple minus exercise, and they'll put in these Weyl parameters. Um, so there's more detail when dealing with this, right? So you notice they have an additional part over here in the equations to actually find this um the liability. And then we've looked at this, but you notice there's a more modified formula, and they've included more impacts where they relate load, life, and reliability. We basically looked at a bit of life, um, and then that was to do with the probability. So I do recommend going over this. Of course, your career, you should probably go over a few of these things, and they even have some additional approximation using the root of the reliability. And this is the combined radial load and thrust loading, right? The loading we did, the same factors, same applies over here. And the X and Y factors depend on geometry and construction of the specific bearing. And same tables apply. Can you see the deep groove, angular contact, what they call the dynamic C10, and then your static C0. Again, they talk about self-lining bearings that will V of equals 1. You know, they talk it's all the same things. You've got your life, and this is a very nice example to do over here. It's exactly the same. Just have to convert your values, obviously, to your SI, and then here they talk about variable loading. So we don't touch this. So this is the next step for bearings as well, where you actually look at variable loading now, right? Where it's not a consistent load, and that's a whole nother extra domain of work. But now I want us to do a quick selection of a ball or cylindrical bearing, right? And what I'm going to do is use this example from the Ansel textbook. Okay. And it's coming from the project. But this procedure is of critical importance because it is basically the way you want to select a bearing, right? So I'm going to just pull up the case study, and then I'm going to show you what it roughly looks like. So in the question, you notice at 10.6, they had to design a shaft, right? And once a shaft was designed, we need to now select a bearing for this. That shaft, if you've checked the project, it looks like this. It comes from this essential figure. Okay, so let me just put that up somewhere here as well so we can see. Oh, let's paste it here. Can I paste it over here? Can you mind? Yeah, that's a shaft, right? Of course, it's going to assist you with the project. So it's the same standard stuff in shaft design. And we know the one bearing is there, the other bearing is there over there. Can you see there? And we assume that the reactions are found already. That's what's key. Okay. Based on that, what we're going to do, right, is we need to decide on what bearing to to find. And how we're going to find it is we go to A, we find the resultant of the two reactions. That's the first step. We do that over there. That's fairly simple, right? 42, 115.4, we get that answer of 122.8. We didn't do the same for RDB. On that side, all the forces acting on the bearing. I'm sure you remember the vertical and horizontal. We find that forces. Once we get that, we find the resultant of those two. So then for us to choose our bearing, what we decide then is to go with the one with a higher load. Obviously, you can design each bearing differently, but we might as well choose a bearing which is stronger, right? That's what you wanna do anyway. So it's just easier instead of buying two different bearings. Yeah, we choose RA to analyze to select the bearing, right? Of course, through our bearing equation, we know there's no actual force on the shaft, therefore it's zero. If there's actual thrust or force, we know we must include it. So that makes our this equation over here, where is it? A lot simple. So that goes away. We're only left with this part over here, right? Or depending on what loading we're dealing with. Once that is done, we then now are able to obviously select our bearing. So what we're going to do, I think I'll take it from here now, in terms of solving. I think that's the easy part. We all can imagine from there. So we're going to say, let me just take it from the project so it's easy to see. We can then just, we apply this exactly the same thing. So like that, our form has been reduced. FR is 122. It's based on selecting which bearing that was. We take that formula. We've got our rotational factor. The V where it's inner or outer ring. Within our service factor, we've also pulled, depending on the condition of what's happening here. Our shaft diameter is 12. We have that, and the rating life is 13. These you're gonna have to specify this part here because depending how long you want the bearing to last, this can obviously affect everything else. Also, we are saying subjected to light shock loading, right? We always apply a factor of safety, but higher than what we require for loading. This is a crane, right? So we know there's some bit of shock happening. We pull the same procedures as before. We get our X and Y factor. We've got V1, we take the X, we plug it in here, we plug all those values in. We get our equivalent radial load of 182. Once you get that, we take our equation over here, right? So before, you had a life as the main variable in which you want to solve, but you want to manipulate this so that C, right, is now the equation, the subject of the equation. Once you do that, you want to input all the values. So P would be your radial load. The life was given as 30,000, right? So that's given to you. We know 1/3. That is your deep groove, your ball bearing. 10 to the power 6, you got your rotational speed. You compute and you get C. And you'll notice you get a value of 2.69 kilonewtons. So once you have the actual load, right, you then have to go to the table. So this table, and based on your size of your shaft, which is 12, right? Remember, that's important. We then go look at which bearing we select. So if you look at the bore of 12, I think we can select this bearing over here, a 02 series ball bearing, right? Yeah, and we can select that one and with those parameters. So if I look at that question, did they select the same? Yeah, 0.2 with a bore 12 has a low rating of 3.189. And that's well above the estimated 2.69 we've gotten, and the bearing is quite satisfactory. So what's key is that we're choosing a load greater than that. So if I revert back to that, you'll notice that 12, bore 12, yeah, choose on the dynamic value, and we more than sorted. What we could have done is, wow, let's look at our angular contact as well. And that's also sufficient. You could also choose that bearing as well. For that, you could have even looked at your ball bearings, your roller bearings as well, and you could look at that catalog and done a similar selection to see whether the bearing would be sufficient or not. So that's the actual way of doing selecting bearings, where you actually look at the loads and and based on the load, you check the bearing catalog, and then obviously you select the bearing then. So that's what's key over there. Um, and also when you're dealing with a different type of bearing, like when you're looking at your your angular, your tapered roller bearing, that's a whole another, you know. Otherwise, what's also cool is that you can also use the website of the particular bearing manufacturer, and that could you could use that as well to 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 yeah. And then to close off that, um, you also I want to mention things of lubrication as well, because you do lubricate rolling bearings as well. And what's key is that we can either use grease or we can use oil, and these are the conditions based on when. So on high speeds, we typically going to use the oil. Lower speeds, you want to use the grease, right? Depending. So like on the main bearing shaft of a propeller or engine, diesel engine on the ship, you want to go with a lower speed. Whereas you're going with something quite fast, like in a car, on one of the drive shafts, you maybe want to use oil. And what I like what they say, I mean, the purposes of the lubricant again is to provide a film of lubricant between the sliding and rolling surfaces, just as before. What's also key to help distribute heat, anticipate heat, and prevent corrosion, and also to protect the parts from foreign matter. So again, Shigley does, I believe, a lot better job than the Ansel book, with a lot of detail in terms of bearing selection. And if you want to challenge yourself, um, there's a good problem here. You can let me know. Um, if you're able to, if I would like to see you guys try and do it where you are, I think it's 11:30, this one, 31, right? Um, one of these problems where you can actually select a bearing. Um, Not critical for the up and coming midterm, but just thought I'd mention it. All right, guys, I hope you gonna learn something from this. And then yeah, I'll see you guys in class. Cheers.